Welcome everyone to the Spring 2022 Environmental Resilience Speaker Series jointly presented by Indiana University's Integrated Program in the Environment and the Environmental Resilience Institute. I'm Sarah Mincy, Director of the Integrated Program in the Environment and Managing Director for the Environmental Resilience Institute. And I'm really pleased that you could join us today. Before we begin, I wish to acknowledge and honor the Indigenous communities native to this region and recognize that Indiana University Bloomington is built on Indigenous homelands and resources. We recognize the Miami, Delaware, Potawatomi, and Shawnee people as past, present, and future caretakers of this land. Both IPE and ERI are motivated to facilitate conversations with today's leading environmental resilience experts from across the disciplines to address topics from climate change to the socio-environmental challenges that are affecting our health and our communities and our economy around the world. IPE was founded in 2012 by the provost and the leadership of the O'Neill School, the College of Arts and Sciences, and the School of Public Health to bring together all of the environmental and sustainability scholarship across the various schools and departments on the Bloomington campus. ERI was founded in 2017 as a part of the IU Prepared for Environmental Change Grand Challenge. Its mission is to co-create environmental resilience and climate solutions through integrated research, education, and community. IPE and ERI faculty and staff and students have worked together to bring you a robust set of speakers this semester, pretty much every other Friday at noon. You'll be able to find information about each of these talks on the ERI and IPE web pages and in our regular newsletters and upcoming event notices that our organizations regularly send out. And we encourage you to sign up for our newsletters so you will get reminders about these upcoming talks, as well as other news and events that we are publicizing. Finally, a couple important logistical notes. Please put your questions for today's speaker into the chat box as you think of them. I'll monitor those and we'll be able to offer those questions to our speaker at the end. And at long last, please let me introduce to you today's distinguished speaker, Dr. Ben Kravitz. Dr. Kravitz is an assistant professor in the Department of Earth and Atmospheric Sciences at Indiana University. He holds a BA in mathematics from Northwestern University, an MS in mathematics from Purdue University, and an MS and PhD in atmospheric science from Rutgers University. He completed a postdoctoral research position at the Carnegie Institution for Science and another postdoctoral research position at Pacific Northwest National Laboratory, where he became a staff scientist in 2015. He joined the faculty at Indiana University in 2019, maintaining a joint appointment at Pacific Northwest National Laboratory. Dr. Kravitz is an international expert in climate model simulations of climate engineering. As the co-founder and longtime chair of the Geoengineering Model Intercomparison Project, he was responsible for coordinating simulations of standardized climate engineering scenarios and enabling access of the data to the international research community. He has served as a contributing author to the 5th and 6th assessment reports of the Intergovernmental Panel on Climate Change, and his work was prominently featured in a recent US National Academies report on designing a federal research agenda for climate engineering. Ben, it's wonderful to have you here today, and the floor is yours.
All right, thank you. And I would like to dedicate this talk to all of the brave souls who decided to show up on the Friday right before spring break. I really appreciate it. So I will dive in. And I'm going to talk about geoengineering or climate engineering. I'll tell you what that means, don't worry. So could geoengineering help improve climate resilience? So I always like to start with this. I don't need to give this audience this background, but I always like to anyway. Climate change in 10 words. It's real, it's us, it's bad. Scientists agree, there's hope. And one of the reasons that I give this talk is because of the last one. People are kind of worried about that last one, and for good reason. So this is a figure now from a while ago, but I don't think it's that different. This was a bunch of Monte Carlo simulations set where they looked at what's the probability that we could stay within a certain temperature threshold. So everything in gray is below 2 degrees, which is the Paris Accords agreement for dangerous anthropogenic interference. Everything above 2 degrees is in orange, and that's where we don't want to be according to that agreement. So a no policy scenario is basically there's no chance of staying below 2 degrees, and there's a very low chance of staying below 3 degrees. Thankfully, we're doing better than that. We do have a world climate policy, in large part due to the Paris Accord. But even with a low policy, the situation's not looking good. If we meet our Paris pledges, then that's the middle one there, the Paris continued ambition. We could stay below 2 degrees C. It's about an 8% chance. I'm not a gambling person, but if I were, I wouldn't like those odds. Paris increased ambition is where we meet the Paris Accord, then we meet back up and we do more. That's starting to look a little better, but still not great odds, as you can see from an illustrated 50% below. So people are, I think, rightfully worried about this sort of thing. So this is GISS temp. This shows the problem. Temperatures going up, we know that one. But also it doesn't go up uniformly. There are some dips, there's year-to-year variability. And there are a couple of things that I specifically want to point out. Those two. So in 1963, there was the volcanic eruption of Agon. And in 1991, there was the eruption of Mount Pinatubo. And we see that the climate cooled for a couple of years after those eruptions. So volcanoes put a bunch of stuff in the atmosphere. One of the things that they put in the atmosphere is sulfur dioxide. And if there's an explosive enough volcanic eruption that can put enough sulfur dioxide up into the stratosphere, it can oxidize and turn into sulfate aerosols, which are highly reflective. They reflect sunlight back to space, it reduces the energy input into the Earth, and it cools the planet. So the idea was that if nature can do this just sometimes by itself, maybe we can do it on purpose. So that's what we mean when we talk about geoengineering or climate engineering. It's deliberate intervention in the climate system. Historically, this has sort of covered two different categories of technologies. One is to reflect sunlight back to space and reduce the energy input into the system. And one is to capture carbon dioxide, pull it out of the atmosphere and pump it back underground into the rock formations where we got the carbon in the first place, or saline aquifers or something like that. So there are lots of ideas that fall under these categories. The ones that I've been working on are mostly the ones in the top left and top right. So increased reflectivity from aerosols pumped into the atmosphere, that's mimicking a volcano, and increased reflectivity from low clouds. So if you spray salt into certain types of clouds with certain characteristics, they can become brighter. And we have observational and theoretical evidence for that as well. So those are where I spend a lot of my research time. I'll get to more of that in just a bit. But first, I want to talk about what's the role of geoengineering? What are we talking about here? So on the left is how I usually like to talk about geoengineering. We've got climate impacts on the y-axis, time on the x-axis. These are deliberately unlabeled because I'm terrible at predicting the future. So in the red is business as usual. And as we know, if we keep emitting greenhouse gases, the impacts are going to go up with time. We can cut emissions aggressively, and we have to. That's the only permanent solution to climate change. We have to stop treating the atmosphere like a sewer. But that won't reduce the climate impacts. It will just stop them from getting worse, because a healthy portion of the greenhouse gas emissions that we put into the atmosphere are effectively permanent. Then there's the green line, where we could actually take carbon out of the atmosphere and put it underground. And that will reduce the impacts. That will actually reverse a lot of the effects of climate change. The issue is it's slow, it's expensive, and it's never been demonstrated at the trillions of tons scale that we would need to demonstrate, because that's how much we're emitting right now. So what do we do in the meantime? Let's say there's a dangerous level and we're going to overshoot it, like in this figure. Do we just suffer? Do we live with it? Do we do geoengineering? Do we do some combination of the two? What do we do? And so that's the idea that I see That's the role I see for geoengineering, a temporary means with a deliberate exit strategy. We sometimes call that peak shaving. So on the right is what we don't want to do. So if we just have business as usual, just keep emitting, and the only thing we do is geoengineering, we would have to do more and more geoengineering forever. And we better not stop, because we're not pulling the greenhouse gases out of the atmosphere. So if we stop geoengineering, all the aerosols will fall out in a few years, and then the climate will rapidly rebound. So that one's bad. So leads into some of my biggest fears about geoengineering. People who think it will solve all our problems. That's the figure that I just crossed out on the right. We don't want to do that. Unnecessary geoengineering. So that figure on the left that I just showed you had no numbers, but you can't design a policy around that. What are the right numbers? What's the right combination of all of these different things? And what does right even mean? Who gets to decide that? Poorly done geoengineering. We could go out and put a bunch of sulfur in the atmosphere tomorrow really poorly and not have a great idea of what it would do. That's not good enough. So poorly deployed, the objectives are poorly met, lots of side effects. These are all things that we would want to avoid if we could. And also, there's been a lot of talk about geoengineering just being a total non-starter. We can't even consider this because it's risky. Well, so is climate change. And I think we need to have that conversation and do those calculations and figure out where the risks lie, compare the benefits and risks, compare the risks of doing geoengineering versus not doing geoengineering. So all of these are research questions. They're things that we need to figure out, because geoengineering is being talked about. It's being talked about at multiple governmental levels. So someday someone's going to come up with a decision for this. Should we do this or should we not do this? And I want that decision to be well informed. So what I'm going to talk about. Mostly stratospheric aerosol geoengineering. So that idea of mimicking a volcanic eruption. Mostly climate model simulations, because that's what I do. And also nobody's ever done geoengineering in the real world, thankfully. And so models are something that we have to rely on in this case. Mostly work I was involved with or where I see the field going, because it's the stuff I'm most familiar with. I will bring in other people's work as relevant. And everything I'm talking about involves a demonstration, more or less. There's a lot of future work in here. We haven't solved the problem, but we're making some strides. I am not going to talk much about ethics, politics, or governance. There are very smart people working on those questions. I am not working on those questions, so I know some things about them, but I am not in any way stating what geoengineering should be designed to do. And to a large degree, I'm staying away from that word should. I'm not going to talk about whether it's a good idea to do geoengineering. I can answer questions about that later in the Q&A part, but that's not what my talk is about. I'm not going to talk about how popular or unpopular this might be amongst policymakers. And I started putting this line in the previous federal administration, and I think it's still applicable. So here's a question that I get a lot, which is relevant for resilience. If we did geoengineering, what would happen? Could this actually be a strategy that could help us with resilience? This is my favorite answer in climate change, my favorite answer when I'm teaching. It depends. So let me show you some figures. This is a plot from the Geoengineering Model Intercomparison Project, where we got a bunch of climate modeling centers from around the world to all do the same simulations so we could try to figure out, what are all the models saying? If all the models agree on something, that's really useful to know. If the models disagree, that tells us we need to spend some time understanding this part. So this is a simulation where we increased CO2 and we turned down the sun. You can do that in climate models. It represents some of the aspects of stratospheric aerosols pretty well. It misses some aspects, but what's nice is that every model can do this, no matter how complicated or uncomplicated it is. So it's a great way to get robust results. And what you're seeing here is the time average temperature results. So this is an average over all 12 models showing what happens when you increase CO2 and turn down the sun, so that global mean temperature is unchanged. And what you get is that geoengineering overcools the tropics and undercools the poles. The stippling is where the models don't agree on the sign of the response. So you can see they agree pretty much everywhere. We're pretty sure that we understand this one. And in climate models, this is fairly easy to understand. CO2 is everywhere. The sun has a latitude dependence. So if you want to achieve no global mean change, you have to, this pattern will result. So this is from turning down the sun. If we do this with stratospheric aerosols, we get a similar answer, but it's not entirely identical. So these are two different ways of doing this. On the right is sulfur dioxide injection at the equator. So we put it up at the equator and we let the atmosphere just blow it around. The atmosphere is basically a giant pump that moves things from the tropics to the poles. So we thought, well, let's just put it in the tropics and let the atmosphere move it for us. And so on the right, you see that really similar pattern, overcooling of the tropics and undercooling of the poles. On the left, we did sulfur dioxide injection at 4 different latitudes, and I'll show you what those are later. But we get a slightly different pattern. The residual warming at the poles and cooling in the tropics is a little bit ameliorated, and there's a reason for that. That's why we designed this simulation. So I'll come back to why these are different and what that might mean for geoengineering studies. Here's another one, increase CO2 and turn down the sun. So this is looking at precipitation now. And again, this is a 12 model average. So on the right there is that simulation where we increase CO2 and we turn down the sun. And what you see is you get an over drying in the tropics. So there's a reduction in tropical precipitation. And if you just saw that panel on the right and nothing else, you might say, oh, wow, that's bad. We don't want that because people like precipitation. But the important thing in here is you have to compare it to the baseline. So on the left is the high CO2 world without geoengineering. And you look at massive acceleration of the hydrologic cycle in a lot of places and some drying in the mid latitudes. So it's important to look at these side by side because you have to compare them. Because we're not talking about just doing geoengineering for the hell of it. We're talking about doing geoengineering in the context of climate change. And again, here are these simulations where we did stratospheric sulfate aerosol, so SO2 injection, and we get some different patterns. So there's a lot more regional effects that are worth paying attention to. You might not necessarily want to believe any individual grid point because after all, this is a model, but the overall general patterns are probably about right. So we see shifts in precipitation in the tropics. Some of these, there's some drying and some wettening in various places. So it's kind of a mixed picture, but we overall see that turning down the sun is an okay approximation for some of these features. Here's sea ice. We might want to care about that too. So this is just one model, but the blue line is the baseline, high CO2 world, no geoengineering. September sea ice in the Arctic is the top right there. That's what we usually look at for the minimum extent. Sea ice is gone by 2040 in the high CO2 scenario. The orange and black lines are the 2 different geoengineering scenarios that I talked with you about. They're actually pretty good at saving and in some cases restoring sea ice. So, you know, it's important to look at a bunch of different things when you're talking about this. It's not just temperature, it's not just precipitation, it's everything. And thankfully, climate models can help with that. So this is a really complicated figure looking at the effectiveness of geoengineering under different metrics. So on the left is precipitation minus evaporation. It's sort of an approximation of water availability. So how much of that precipitation do you actually get to keep? And on the right is maximum 5-day precipitation, which is an okay approximation for flooding events. So I won't go into too many details on this, but basically every pixel is a grid point in the model over land, so where people could live. Everything in blue means the effects of climate change are moderated. Everything in red means the effects of climate change are exacerbated. So climate change makes something bad and geoengineering makes it worse. And what you can see is that most of the dots are in the blue. Actually, over 99% of the dots are in the blue. So geoengineering, by these metrics, if you do just a moderate amount of geoengineering, it sort of looks pretty good for a lot of land regions. Now, you can see there are some land regions that are in the red, and those land regions are certainly important. So I can't just say that geoengineering will basically help everybody and we'll just worry about the other people who aren't helped. That's not going to fly. But it is an interesting result. So, according to model simulations of solar dimming and to some extent stratospheric aerosols, is geoengineering perfect? No. Could it help? Yes. And maybe it could help a lot. So what's the optimal amount of geoengineering? Well, my favorite answer, it depends. It's really hard to answer. And the reason it depends is because I only showed you like 3 or 4 variables. I'm skipping a lot of really important stuff: hydrologic cycle, ecosystems, agriculture, ocean acidification, water security. I'll come back to some stuff along those lines, but all of these are really important and I want to acknowledge that. So many past simulations, including the ones that I just showed you, we did geoengineering in a certain way. So we increased CO2 under some background scenario, and we did such and such amount of geoengineering. And then we basically said, all right, what's going to happen? What will happen if we do geoengineering? And that's useful for learning about the climate system, but the problem is it doesn't end. What if you tweak the background scenario just a little bit and did something slightly different? Or what if you did geoengineering in a slightly different way? If you did it here instead of here, or if you did a little bit less or a little bit more. There are infinitely many scenarios, and it's a never-ending process. So we can't answer the question, what will happen if we do geoengineering? Because the answers really depend on how you do it. We need a more explicit job. We need to do a more explicit job of turning this question around. Can geoengineering do what we want it to do? I'm not going to say who we are, but basically, what's the space of achievable climates? What can geoengineering do and what can it not do? Also, how can we manage uncertainties? Because if the idea of geoengineering scares you, good, it should. It is kind of scary to talk about deliberately interfering with the climate system. And you might say, well, there's a whole lot we don't know. But so that talks about uncertainties. Some of those uncertainties we can reduce with research. Some other uncertainties we can't. So can we manage them? And I'll show you what we mean by that. So the bottom line here is that geoengineering can be designed to some degree. And I'll show you an example. So these are 12 models that simulated those solar dimming experiments. So on the top right there is the high CO2 world. And on the left where the lines are going through, that G1 minus 1850, that's high CO2 plus solar dimming. If geoengineering were a perfect offset, then everything would be right at the origin of this figure. So they're not. If you increase CO2 and then you turn down the sun, you can offset global mean temperature change, but you over dry the planet. And so here are the results from 12 models. Now, what we could also do is we could say, well, I don't like over drying the planet. So maybe I'm okay with a slightly warmer world that doesn't over dry. So instead of going all the way down to the x-axis, I might stop at the y-axis, which is slightly warmer, but not over dry. Or I might just do a little geoengineering. I'm going to stay in the top right quadrant, but I'm going to move them a little bit. Or maybe I want to stay in the top left quadrant and I'll just sort of split the difference between two scenarios. The point being, there are many possible climates that could result depending on how much you turn down the sun or how much geoengineering you do. Here's another example. It's kind of a complicated figure, but in this one, we played with solar reduction as a function of latitude or in different seasons. So what if you turn down the sun more in the northern hemisphere than the southern hemisphere, or more at the poles than in the tropics to offset that overcooling of the tropics and undercooling of the poles? Or what if you only wanted to geoengineer in summer, northern hemisphere summer, because you're worried about monsoon precipitation? So what we show on the right is different combinations of those. So that star that says pre-industrial baseline, that's where we were starting for, just two metrics that we picked that could be important. So tropical precipitation and northern hemisphere September sea ice. The high CO2 world is that filled in black star. And then if we only turn up or down the sun uniformly, we can travel anywhere along that black line. So that's what the uniform means. So, the amount of geoengineering is a knob that we could play with. But if we start to bring in latitude and season, we can travel anywhere in that shaded gray area, just through combinations of different latitudes or different seasons. So that really starts to open up the space of what geoengineering might be able to do. And this is really important for negotiations on geoengineering. So if a policymaker comes to me and says, all right, we all talked it over. This is not going to happen, by the way. We all talked it over and we said, we want geoengineering to do this. And I look at this chart and I say, okay, that's in the gray area. We can do that, and here's how. If they say we want geoengineering to do this and it's not in the gray area, I'm going to say, that's not going to work. We can't do that. And so those sorts of questions are really important to answer as best we can. So how do we do this? How do we approach geoengineering systematically? So number one, we have to clearly articulate the objectives we're trying to meet. Number two, identify things in the climate system that we want to modify that will affect those objectives. Number three, develop a strategy for how to meet those objectives. And number four, verify the strategy as best we can. So some objectives that people might care about. So here's that plot on the right, again, showing overcooling of the tropics, undercooling of the poles. So some objectives that people might care about. We might care about global mean temperature. It's a proxy for a lot of impacts. But if we reduce global mean temperature, we cool the northern hemisphere more than the southern hemisphere because there's more land in the northern hemisphere. That might shift tropical precipitation because that moves toward the warmer hemisphere. And maybe we don't want that. So maybe we want to target the interhemispheric temperature gradient as well, so we don't shift tropical precipitation. And also, maybe we don't like this undercooling at the poles. Maybe we want to fix that. So we might target the equator to pole temperature gradient. We might want that to be the same as well. So these are three objectives that we could pick. Now, what in the climate system will modify those? So what we found, and this is a complicated figure, you don't have to memorize it, is basically if we inject at 4 different latitudes, we can have 3 independent degrees of freedom. So if we want to inject at 15 degrees north and 15 degrees south, so that's looking at the top left up there. The solid black line is what the combination of those two could get us. And it's not perfectly uniform across the globe, but it's not bad. And so that could help us target global mean temperature. The top right and the bottom left are showing injections at 15 and 30 degrees latitude. We don't have to care about longitude because the winds blow everything around all longitudes. And so latitude is basically all we need to care about. But if you add those two up in various combinations, you can get something that's relatively linear with latitude, increasing northward or southward. And so that can help us with the interhemispheric temperature gradient. And then if we inject only at 30 north and 30 south, we get something vaguely parabolic. And so that could help us with the equator to pole temperature gradient. So meeting all 3 of those objectives can be done with, relatively speaking, with 4 latitudes of injection. Next is the strategy. how do we do this? And so we'll look, okay, SO2 injection at these 4 different locations. Here are the 3 objectives. Well, injection of 30 degrees north affects all of these. Injection of 15 degrees north affects all of these, and so on and so on. Everything affects everything. So how do we figure out what to do? How do you know, okay, I should inject this much at 30 and this much at 15 and this much here and this much here, and that'll magically give us what we want? There are uncertainties in the climate system response. We will never be able to just calculate that. And more to the point, what happens if you do your best to understand the system's responsiveness to forcing, but you get it wrong? Like, we're talking about the planet. You don't just get to say, oops, my bad, and ask for a do-over. It doesn't work that way. So we need a strategy for managing potential for uncertainty. And we call this feedback. These are feedbacks in climate science. These are feedbacks in any system. We do this all the time, and I'll show you. So if I were giving this talk in person, I would normally ask how many of you have ever taken a shower? And I would then tell you it's okay to lie, because I don't really want to know. Let's just assume everyone has. So this is how you engineer a system that you don't understand. You use feedback. If you take, let's say you're staying in a hotel, you have no idea where to set the shower knob that's the right temperature. So you turn it on somewhere, then you stick your hand under. Okay, too cold, adjust, stick your hand under. Okay, a little bit too warm, but it's getting there. Turn it back a little bit, stick your hand under. Okay, we're good to go. That's a feedback loop based on observations of the system. For the engineers in the audience, here's a block diagram. So the amount of injection is based on how far we are from our goals in previous years. We used proportional integral control. It's not that complicated. Why feedback? Why do we need feedback? Well, if you know the system perfectly, you don't need feedback. You just compute the response. When you're showering at home, you know exactly where to set the knob because you understand the system. You don't have to fiddle with it. You just set it. And I said this before, but I'll say this again. We need feedback because we don't get do-overs. We have, if this is going to be done, we have to get it right the first time. So if you don't know everything, feedback works better. And here's an example. So the solid black line is a scenario of climate change, vaguely similar to the Paris agreements. And let's say we want to go from, so that's global mean temperature. Let's say we want to go from the solid line and we want to keep everything at the dotted line. So you could do this 2 ways in a climate model. The predictive way is where you say, okay, I know this model really well. I've run this model hundreds of times. I'm going to look at this curve, the solid curve, and I'm going to say, here's how much geoengineering I should do in each year. I'm going to program it into the model and click go. So that's the blue line that I'm going to show you. The red line that I'm going to show you is using feedback, where every year we look at how far are we from the dashed line, and then we adjust the amount of injection every year. So there's the blue line. It's pretty terrible. We kind of get close in the late 2070s, but that's maybe more by chance than anything else. It's just not very good. There's the feedback run. This works, and it works really well. So I'll show you a more complicated example. Here is where, against the background of a very pessimistic climate change scenario, we used feedback by injecting at each of those 4 different latitudes. You can see that on the bottom, to try to meet the 3 objectives. So global mean temperature is on the top, and in the middle are the interhemispheric temperature gradient and the equator to pole temperature gradient. We want everything to be on the dashed line. And it works. And this is a state-of-the-art climate model. This is as complicated as it gets, but it worked. So you can see how much injection we have in any given year from the bottom panel. Let me show you a video that NCAR put together of these simulations. So this is false color, but you can see the sort of cloudy stuff are the aerosols. So this is before injection. What you're seeing is just the background aerosol layer. And right about now, we're going to start injecting. The algorithm just called for injection in the northern hemisphere in that year, so that's what it's doing. So you can see the aerosols are injected in one location and then they spread. And now the algorithm calls for injection in the southern hemisphere. So again, just one location, and you can see it spread throughout the entire model. And so again, this is false color. This is not what it would look like, but you can see the algorithm adjusts the injection every year based on how far we are from the previous objectives, from the objectives in any given year. So that's how it works. I'll let the video run just because it's really cool and I can't bring myself to stop it midway. NCAR has a really nice team that can do visualizations of climate model simulations. So, and then here's a static picture of that. So showing both, so that simulation that we did is called GLENS. It stands for the Geoengineering Large Ensemble, because we didn't just do one simulation, we did 20 of them. And that's available to the community. In the orange is the equatorial run, where we just tried to meet global mean temperature by injecting at the equator. So GLENS works pretty well. You can see the black lines meet the objectives pretty well. That's in the annual mean. So let's talk a little bit more about season. So what you're seeing here, each row, you can see the labels on the left, each row is injection at a different latitude, and each column is injection at a different season. So December, January, February, March, April, May, June, July, August, September, October, November, and then on the far right is annual injection. And you don't have to memorize what each of these is, but the point being, they're all different. If you inject at different latitudes and different seasons, you get different aerosol coverage. So that could potentially be used to our advantage in designing a strategy for geoengineering. And let me show you some results from that. So this is looking at, so the middle panel is temperature changes in the Tibetan Plateau. That's that red box up in the top there. And in the bottom is land precipitation changes in India. So that's the black box there. And these are 3 simulations. So the blue one is injection all year round. The red one is injection just in autumn. And the green one is injection just in spring. And so what we can see is that just in, so we want everything to be along the solid black line there. That's the 0 line. That means no change from the baseline. So what we can see is that the red line is a lot closer to that black line than the others are. So season of injection can really change the outcomes. Now, what I'm not showing you is the Amazon. That one prefers the spring instead of the autumn. So this starts to get very complicated because, how do you choose? And I also want to emphasize that these are results from one model. Mileage may vary. We're actually working on that right now, trying to look at 3 different models and do they say different things. But here's some things that we know. There are independent objectives. So one of the sort of memes that I hear at conferences is whose hand is on the thermostat? How are you going to get the UN to agree on a global mean temperature? Well, you're not. But you don't have to get them to agree on just one thing. You might have to get them to agree on 7 things, which is still a really hard job, but it's, it takes on a different character. So there are independent things in the climate system that we know of. You could do all of these simultaneously. So restoring sea ice, shifting tropical precipitation, or preventing a shift in tropical precipitation, preventing changes in the equator to pole temperature gradient so you don't get that overcooling of the tropics and undercooling of the poles, and offsetting changes in global mean temperature. Here are some objectives that we know will interfere with each other. So I showed you this before. If you offset global mean temperature change, you overdry the planet. If you don't want to overdry the planet, you have to settle with something that's a little warmer. So those interfere with each other. You cannot just cool one hemisphere and expect that tropical precipitation won't shift. Tropical precipitation always moves toward the warmer hemisphere. There are others. I'm not going to claim this is exhaustive. So that was step 3. Step 4, independent verification of the strategy. How do you do that? with geoengineering? What's our basis for evidence? So observations, we don't have them. We do have observations of volcanic eruptions, which are useful, but to some degree limited. Theory, this one we have. We know that if you put sulfur dioxide up in the atmosphere, it's going to cool the planet. We know that if you put it more in the northern hemisphere, it's going to cool the northern hemisphere more, etc. So we do have some theory. To a large degree, our basis for evidence in geoengineering is models, an over-reliance on models. So how can we use that to independently verify the strategy? How do we know that we're right when I show you these results? Well, you can do the same simulations in a different model. It's not perfect because both models could be wrong, but it helps. So where are we headed? Ultimately, what can geoengineering do and what can it not do? Can we put numbers on this figure? What are the possible objectives? What sorts of climate impacts can we offset with geoengineering? And is that a good idea? And how do we get to questions of resilience? So this is a sort of model of the geoengineering timeline. So right now we are in the research phase. We're doing model-based research. There are people talking about process-level field experiments. Nobody's ever done a perturbational field experiment. People are looking at satellite instruments to measure volcanic eruptions or something like that. At a certain point, there's this kind of bright line where we would move from research into operations if people decide, yes, we want to do this. And then we start moving into things like forecast modeling, monitoring, pre-deployment activities where we start injecting something into the atmosphere with the idea that if this goes well and doesn't reveal major problems, we're just going to keep doing it and start ramping up. And so where's that line? What's that transition period? What information do we need to make that go, no-go decision? And that's where I think mission-driven research comes in. So this is what I call a risk register. This is from engineering. So on the x-axis is the probability of being wrong. On the y-axis, the consequences of being wrong. Anything in the top right is a high priority research question. So we need to figure out which uncertainties belong up there. My colleagues and I took a first cut at this just based on what we know. So we suspect that uncertainties in aerosol microphysics are really important. Subgrid scale mixing is also really important. So in the models, we take the SO2, sulfur dioxide, and we put it in a grid box and we say, model go, you blow it around. Well, a grid box is like 100 kilometers on the side. So what happens on that below 100 kilometer scale? Does the SO2 actually disperse the way we think it does? Or does it just all glom together and sink like a stone because the stratosphere has weird properties? So getting that subgrid scale mixing could be really important. It could be answer changing. And so that's a major area of research that we've identified. Looking at the bottom, ecosystem response. Geoengineering would affect ecosystems. Climate change is affecting ecosystems. And to a large degree, we don't understand it. So that seems like a very high priority research question. And I also like to highlight that one because we can't talk about risks of geoengineering without talking about the counterfactual. We have to talk about climate change. Is this better or worse than climate change? Well, I don't know. We better figure that out. So I'll wrap up and then I see a bunch of questions popping up, so we'll shift to that. Geoengineering is not a permanent solution to climate change. We have to stop putting greenhouse gases in the atmosphere. There's a lot we don't know. If this is going to be considered, we need to fix that. And also, I'm not presuming the answer here. One of the outcomes of research could be, wow, geoengineering is just totally unworkable. We can never do it. We need to know, so we stop working on this and start working on other things. There's an important role for understanding if we do geoengineering in this way, what would happen? We also need to ask what it can and cannot do. At some point, climate models are going to be limited. We can't do everything with climate models. And so what are those limits? Because that will help us figure out what field experiments do we need to answer which uncertainties, and do we want to actually do those field experiments? Anything involving people, really hard, really important. I did not talk a lot about that. Basically, there's a lot to do. So that's all I've got.
And that was fascinating. Thank you so much. I have learned so much, and we have an array of great questions. I'm going to start with something that's pretty basic. You talk about how you implement geoengineering at different locations and different seasons versus uniform, but really on the ground, practically, how do you accomplish these injections? I'm having trouble imagining the scale that and how you do this, whether it would replicate a volcanic explosion. Can you talk a little bit about how we implement that?
I even have some backup slides for that. So is this possible? On the right is just sort of a graphical representation of some ideas that were thrown out there. A lot of these ideas are taken from a 1992 National Academies report. So using a very tall tower to pump stuff up there, flying airplanes up there and just opening the back, weather balloons, artillery shells. Ultimately, after talking with a bunch of experts, the only one of these that actually makes sense is airplanes. And it's going to be probably a new airplane design. So I'm working with a colleague who spent his life in the aerospace industry. He was an executive at Boeing, then he had an airplane retrofitting company, and now he's just interested in this stuff. So it would be a new design. It's not a radically new technology. It would just require a new airplane. So based on those sorts of costs, cooling the planet by a degree would cost about $10 to $100 billion a year. Now, I don't have that. Jeff Bezos does, but if he did this, he would be broke in a few years. But it's cheaper than a lot of the numbers that I see for mitigation or carbon dioxide removal. So that's kind of what we're talking about.
Great. And then another kind of basic question, is this the under a white sky scenario? Does the sky look different?
I actually wrote that paper, so I can answer that one. Not really. So, I mean, when I was writing that paper, I learned a lot about different color perception, like what you call blue and what I call blue are probably very different things. But fundamentally, the answer is, if you go to New York City or Chicago, is the sky still blue? Yeah, it is. So it might be a paler blue, but it's still blue. That's kind of what we're talking about.
Okay, great. We had a couple questions about acidification. What concerns do you have about the sulfates falling back down to the earth after a few years? Acid rain concerns, and I think this is close enough. How much worse does ocean acidification get?
Yeah, so the sort of things that we're talking about, cooling the planet by about 1 degree Celsius is generally what people are talking about, maybe 2 degrees. So a degree Celsius would take about 10 teragrams of sulfur dioxide per year, which if you do the stoichiometry is about 5 teragrams of just the sulfur part. So what we are putting in now as part of industrial pollution is about 130. So 5 out of 130, it's not a huge increase. Very sensitive ecosystems might notice, but that's about it. This would not affect ocean acidification whatsoever. It's just too small.
Going to modeling, how much does the phenomenon of ENSO, I think that's La Nina and El Nino, complicate the feedback and adjustment process? Wouldn't this need to be continually adaptive?
Yeah, so I mean, that's one of the neat things about feedback is it responds to the temperature difference from the goal, whatever's causing it. So it responds to natural variability too. And I mean, another example that I think about is driving your car. Like, so when you drive your car to work, you don't sit down and map out, okay, there's a curve here, there's a pothole here, my crazy neighbor is going to come shooting out of their driveway at exactly this time, so I need to plan for all of those things. You just respond to what's out there. You turn left, you turn right, you stop. And so that's the same idea here. Feedback responds to natural variability. And I can go into various theorems about how feedback actually affects natural variability. It does suppress it in some frequencies and amplify it in others, but you don't have to understand why the temperature is different. You just have to understand how sensitive is the system to what I'm doing to it.
And would this affect the jet stream?
For sure. Yeah. Anytime you put anything in the stratosphere, so these aerosols would heat the stratosphere. They absorb radiation from the Earth and then they would heat things up, and that will change winds. And that has important stratospheric effects, that has surface climate effects. So some of the results that I showed you have those in there. And so, that's another side effect that needs to be taken into account.
And that would be including polar vortexes might be more common, destabilization of the polar cell.
It would actually strengthen the jet stream. And so maybe polar vortex events would be less common, but I don't know. I haven't really looked into that.
Back to feedbacks, like you just mentioned, feedbacks work well, which I guess means that stratospheric aerosol injection generates a quick response in the atmosphere. But ideally for feedback, you'd want to geoengineer with a system that decays quickly so that it's easy to pull back. Is aerosol injection the best approach for that?
Yeah, that's a great question. So we don't want to do something where we put it up there and say, oops, that was a bad idea, but we got to wait 100 years for it to stop. So the sulfate aerosols, if you stop doing it, would fall out within 3 years. So is that fast enough? Well, it depends on what you're looking at. For marine cloud brightening, which I didn't talk about a lot, the aerosols will fall out within a matter of a week. So that's faster. But also marine clouds aren't everywhere, so you can't brighten everywhere, and maybe you can't brighten everywhere you need to. And so there are a bunch of different trade-offs. People are talking about complementing those two. So you do stratospheric aerosols and marine cloud brightening simultaneously. Very preliminary studies have shown that they kind of complement each other in terms of their effects, but I think there's a lot we don't know.
Speaking of a lot we don't know, you said we need more research in this area, but I'll ask this question, maybe you can talk a little bit more about it. You focused primarily on temperature and precipitation responses, but what do the biogeochemical and ecological responses look like for aerosol injection that we do know about?
We don't. So the first meeting on this stuff that I went to, it was basically just a bunch of volcano experts. We were all atmospheric scientists who were interested in volcanoes and stratospheric dynamics. We finally got our first person working on carbon cycle in 2015. We got ecosystem people interested in 2018. We are so understaffed on this topic. And so we're just kind of doing the best we can. One of the biggest holes, I think, is impacts assessment. So do people care about global mean temperature when they go outside? Not really. They care about things like food security, water security, heat waves. And translating these climate model effects into impacts assessment is something that is, quite frankly, very hard to do even without geoengineering. And so I've said it at every meeting, and I'll continue to say it until we actually do it. That's where I think our biggest gap is.
Well, maybe since you finally got a carbon person on, you can answer this one. What are the life cycle carbon energy impacts for aerosol geoengineering?
It's kind of a few questions. So I am not a carbon cycle expert, so I can't speak too much to that. I can talk a little bit about solar energy. So, and a little bit about carbon cycle in general. So stratospheric aerosols reflect some sunlight back to space, but they also forward scatter. So you get a little bit reduction in total sunlight, but you get a large increase in diffuse light. So plants actually like that because diffuse light can penetrate canopies better than direct sunlight. After the Mount Pinatubo eruption, I think we saw a massive increase in gross primary productivity. And so people are starting to wonder, would we see something similar under geoengineering? And you also get the added benefit of geoengineering would happen in a high CO2 world, but with reduced heat stress. So maybe plants like that, but also, plants like sunlight. And if you're reducing the sunlight, there's less energy. And so it's really complicated to figure out all of those answers. Similarly, it would affect solar power. So like a 1% reduction in total solar irradiance would reduce solar power generation by 1%. That's fine for solar PV. They don't care whether it's diffused or direct. Those concentrating generators for solar energy, they care about direct. So 20–30% reduction maybe. So that needs to be taken into the calculations too.
Along these same lines a bit, what is the greenhouse gas input into this process when we're talking about planes and sulfate manufacturing? Is that considered in the modeling?
That is not considered in our modeling, largely because we do not have a system that can handle those climate society feedbacks in a way that we need them to. There are people in integrated assessment modeling who are working on incorporating geoengineering into it in an effective way. Because the problem with integrated assessment modeling for this topic is they're largely economic models, and so they need a market to solve. And geoengineering is just so cheap by comparison that the models just say, all right, free geoengineering, problem solved. And that's not the right answer. And so you have to incorporate it in a little bit better, and they're working on that. But once that happens, we can actually generate those societal changes that change greenhouse gas emissions that then feed back into the climate. So I'm really looking forward to their results.
Are you aware of any plans to look at ecosystem impacts in closed facilities like Biosphere 2?
I'm not. We do understand to some degree how ecosystems respond to aerosols in general, like pollution. But the problem is it's really hard to replicate stratospheric conditions in a reasonable way. It's like, 20 kilometers up in the atmosphere, harsh sunlight, very low pressures, very low temperatures, very low humidity. You can't build a stratospheric chamber. And so how do you do that and then incorporate the effects it might have on ecosystems is, I remember being at a meeting, 10 years ago now, where we talked about this. And I think the conclusion of that conversation was, yeah, that's really hard. And I don't know if we've progressed beyond that.
Well, Ben, I think I'm going to end it there with a couple minutes to spare. So people who have a 1 o'clock have a little break. I want to thank you so much. This was incredibly fascinating. I've learned so much. I really appreciate your time and energy today. Thank you.
Yeah, thank you. And I'm easy to find, so email me if you have any more questions.
Excellent. And folks, our next Resilience Speaker Talk is on March 25th with Dr. Andrea Jane from IUPUI. So join us then. And if you're going on spring break, enjoy your time away, and otherwise enjoy a break. Thanks, everyone.